record the meeting. Okay, I hope agree lahat, ha? Okay, so let us proceed now. No, our lecture for today's meeting is all about flexural analysis of beams. Okay, basic assumption in flexure theory. Okay, so sections perpendicular to the axis of bending that are plane before bending remain plane, no, after bending. So our section will remain plane, no, after bending. So that is basically what is number one assumption is all about. Number two, the strain in the reinforcement is equal to the strain in the concrete at the same level. So it's actually a linear, no, linear yung relationship between the strain in the reinforcement and in the concrete. Okay, so that is basically what we call compatibility relationship, no, between the reinforcement strain and the concrete strain. Then number three, the stresses in the concrete and reinforcement can be computed from the strain by using the stress-strain curve for concrete and steel. Okay, so in terms of stresses, we're going to consider, no, the stress-strain curve, no, for both concrete and steel. Okay, so that is about the third assumption. Okay, so we have here some figure showing us a beam, no, having a cross section and having a reinforcement. Okay, so the determination of the flexure, no, flexure stress, okay, can be computed using the formula FB equal to MC over I. And this is applicable, no, when you're dealing with the WSD method, you know, the WSD method. So FB is equal to MC over I. So later on, we're going to use this, no? And the derivation of this is actually based from this third figure, no? Making use of the deformation of the cross section of the beam. So I think yung mga naging student ko ng mechanics of deformable bodies, I think I presented, no, a derivation, no, the derivation of the flexure formula, making use of this diagram. Okay. What else? So for this next slide, we're going to consider here the three distinct stages of beam, no, wherein we're going to apply load in a beam, no, and then gradually increasing the load. So the beam will have three distinct stages before it will collapse. Okay, so these three stages are, number one, we have the uncracked concrete stage. So meaning based from a particular load, your beam will not have a crack, no? So it will not crack at the tension side, no? And we can actually measure the tensile stress of the concrete, no, at the tension side. Number two, as the load increases, the concrete will crack. So that is why we have what we call crack, no, crack concrete stage, and this based from elastic stresses stage. So meaning yung yung um, concrete natin behave elastic. So kapag behave elastic yan, it is bounded by allowables, no? Uh, so that is about this stage, and the loads are considered as service load. Kaya nasa service stage siya, no? Kapag service load ka natin, yung ating load are unfactored. So wala kang idadagdag na load, no? Wala kang i-multiply the factor para mag-increase yung load natin. So 1 and 2, the load here are considered as service load. By the way, yung number 1, when your beam is on this uncracked stage, this is considered as uneconomical, no? Bakit uneconomical to? Dahil ayaw mong ma-experience nung beam mo, no, na mag-crack yan. So piniprevent mo na umabot siya dito na or ma-attain niya yung stage na to. Okay, so you're going to make your beam massive. So magiging malaki yung magiging section ng beam mo. Kaya kino-consider itong uneconomical. Okay? Now, yung third stage, as the load increases, aabutin niya yung tinatawag na ultimate strength stage. So dito, no, sineset natin yung beam natin kung saan siya pwedeng mag-fail. Okay? Kaya this is the failure stage of our beam. Okay, so those are the 3 stages. Now for the stage 1, okay, we have the uncracked concrete stage. The design method that we're going to use here is actually the working stress design method. Okay, so the criteria for us to identify if our section or if our beam is on the uncracked concrete stage, all we need is compare. Okay, we simply compare MA and MR. So what is MA? MA is the acting moment. This is the actual moment based from the service load. Okay, so yung actual moment natin, if you're going to compute this, so kung ano yung ginawa nyo sa theory 1 or sa mechanics of deformable bodies, so i-determine mo yung maximum moment, no? So you may use area method, like kunin mo muna yung shear, then kukunin mo yung moment, then you determine the maximum moment. So MA here pertains to the maximum moment based from the service load. So if your acting moment is less than the cracking moment, then no, you have an uncracked section. So uncrack yung section mo. So yun yung ating criteria in determining if our section is uncracked. Another thing, no, another criteria that we may consider, no? Kaya lang ito, pag ito yung ginawa mong criteria, you already computing the stresses in your section. Ito kasing moment, pag ito yung basis mo, ito yung earlier part ng computation mo. Kaya kaagad ma-identify mo. But using the other criteria, you make use of the stresses. So ano yung stresses na yon? Ito, the tensile stress in your concrete, no, is less than the modulus of rupture. So yung modulus of rupture natin is yung FR, no? So if the tensile stress in the concrete is less than the modulus of rupture, then you may also say that you have an uncracked section. Okay? So yun yung ating criteria for the determination of for us to identify if our section is uncracked. Okay, so this is now the showing us the stress strain diagram. For the strain, as mentioned, we can determine the stresses. Okay, we can determine the strain, no, by taking the relationship, no, of the strain in the steel and in the concrete. So we have this diagram showing us the linear relationship, no, of our material, no, in concrete and in our steel. Okay, so epsilon S, this is the strain in our tensile reinforcement. Epsilon C at the top, it represents the strain in the concrete under compression, and epsilon T, it represents the strain in the concrete in tension. Okay, so ito yung ating strain diagram. For the stress diagram, FC represent the stress in concrete in compression. So remember, these are the maximum stresses which is occur at the top, no, if the top is under compression. Now Fs over N is the it represent the equivalent stress of steel, no, which is in tension, and F sub T represent the tension in concrete. Okay, so that is the stress, the tension stress in concrete. So making use of this, we can able to determine the relationship, no, between the stresses, no, in our materials. So that is for the uncracked concrete stage. Okay, for the stage 2, the concrete crack elastic stresses stage, no, as the load is increased, no, after the modulus of rupture of the concrete is exceeded. By the way, the modulus of rupture represent the we make use of this in identifying if our concrete is, if our beam is uncracked, no, as I have mentioned, the tensile stress in the concrete are less than the modulus of rupture. So when this tensile stress, no, is greater than the modulus of rupture, so as mentioned here, if it is exceeded, no, yung section natin, yung concrete section natin, yung pinaka bottom niya, kaya nagkaroon yan ng stress dito, kaya meron pa siyang stress dito kasi hindi pa nagka-crack yung concrete, kaya uncrack kanya, no. That is why you still have a value of the stress in concrete in tension, no. But if this stress exceeded the modulus of rupture, okay, ano yung mangyayari? Cracks begin to develop in the bottom of the beam. So dito sa bottom dito, mag-start ng mag-crack. Pag nag-crack na yung concrete, it has no longer uh, so wala nang stress na madidevelop dyan, no? So that's why your F sub t here eventually becomes zero, no? Okay, because of what it already begins to crack. Okay, so the moment at which these cracks begin to form, when the tensile stress in the bottom of the beam equal the modulus of rupture. Okay, okay, so the moment, no, once these begin to form, yung tensile stress natin is actually equal, no? The tensile stress there is actually equal to the modulus of rupture. So once it is equal to the modulus of rupture, that moment is known as the cracking moment, no? Known as MCR. So as the load is further increased, these cracks quickly spread up to the vicinity of the neutral axis, and then the neutral axis begins to move upward. So yung neutral axis mo, okay, tataas yan. So ibig sabihin, yung usable compressive part ng concrete mo, okay, lumiliit, no? So yung depth ng compressive part ng concrete mo lumiliit. So as the crack spread, no, up to the vicinity of the neutral axis. Okay, so your depth of your neutral axis with respect to the top, wherein we are referring it to the compressive part. So lumiliit yon, no? Lumiliit na. So yun yung mga ma-observe mo kapag nag-crack na yung concrete natin. So the cracks occur at those places along the beam where the actual moment is greater than the cracking moment, no? So ito yung isang criteria for us to know kung crack na yung section natin. Yung acting moment is greater than the cracking moment. So do sa uncrack, balik, no? MA is less than MCR. So kapag nag-crack, nasa crack stage na yung concrete mo o yung beam mo, MA is greater than MCR. Okay? So ano pa yung mga important things na kailangan nating consider dito? Okay, so the stress and strain diagram, ganun pa rin, no? Very linearly pa rin yung relationship nila, no? Even though you already have on the crack stage, the stress strain diagram is still very linearly, no? So straight line pa rin yung relationship. Okay, then we have here the straight line stress strain variation. Okay, in the determination of the stresses, no, in our concrete under crack stage, okay, yung ating mga stresses sa concrete is still they are less than 0.5 F prime C, no? So still less than yan mga yan, no, for us to say na safe, no, yung ating beam, no, dahil kapag stick yung behavior ng beam natin, we are bounded by allowable. And in concrete, ito yung pinaka-allowable natin sa concrete, no? So we have 0.5 F prime C. So yun yung pwede nating i-comparison, no? So they are still less than 0.5 F prime C. To compute the concrete and steel stresses in this range, the transformed area method is used. Nakikita uli ba yung ating presentation? Okay, so yun, no? To determine all of this, no? To determine the stresses, no? We need to make use of the transformed area method. Now, with regards to the last statement here, so I think we are already aware that when our beam is on the crack stage, the acting moment is larger than the cracking moment, no? So it is greater than, okay? And the tensile side of the beam will be cracked, no? So to visualize this, ito yung ating mga illustration, no? Okay, so once na nasa crack stage na yung beam natin, cracks will be developed in the tensile side of our beam. Okay, so ito yon, no? And the strain diagram, ganun pa rin siya, no? Linear pa rin yung relationship between the strain in the concrete and in the steel. Now for the stresses, the relationship of the steel, okay, as you see here, no, is actually linear pa rin naman ito, no? So we can still consider this as a linear, but then again, for the tensile stress in concrete, wala na yan, no? Kasi crack na, no? Crack na kasi yung bottom natin. So yung tensile stress in the concrete is no longer considered, no, dito sa ating stress diagram. Okay? So yun yung ating stage 2, no? Wherein our beam is on the crack stage. So other they identify our section as crack section, no? Pag naman uncrack yan, uncrack section. Okay, the third stage, which is the ultimate strength stage. Okay, the compressive stress in the concrete will be greater than 0.5 F prime C, no? So dun sa stage 2, yung compressive stress natin is still less than 0.5 F prime C, but for ultimate strength stage, okay, so the compressive stress will be greater than 0.5 F prime C. Okay, so here crack will occur at the compressive side, no, of our beam, no, and the cracks at the bottom will go up further, no, will go up further yan. Kaya lalong liliit yung or we can say yung location ng neutral axis nating lalong tataas. So as shown here dito sa ating strain diagram, no? And also the stress diagram in our concrete is no longer linear. So it's actually parabolic in shape, no? Parabolic na yan, no? Okay, yun about the ultimate strength stage. Okay, so yun yung distinct stages ng ating beam at different loading condition. Okay, so in the analysis and design, since we are bounded by, so since we are following codes, no? So these are the minimum requirements, no? These are minimum requirements given by the code. Number one, we have yung spacing limits for reinforcement. So there's a required minimum spacing of the reinforcement. Okay, so if we will draw the position of our reinforcement. Okay, so what is given by the code? The clear spacing between rebar must have what? A minimum of what? 1 inch. No? Kailangan minimum dyan 1 inch. So in metric, it is equivalent to 25 millimeter. So similarly, ganun din to sa vertical clear spacing. Kailangan ang minimum dito ay 1 inch. So 25 mm. So that is the value of the minimum spacing. Now question is, why is it 25 mm or 1 inch ang minimum? Okay, ang pinakadahilan dyan, it is because of what? Because of the gravel, no? So yung gravel do sa concrete, para pag nagbuhos ka, makakapass through yung ating bato. Kasi sa pagdating sa mga beams, no, especially the beams, usually we make use here of gravel size. Ang pinaka size niya nasa 3/4, no? But in case you use 1 inch, I think kailangan mas lakihan mo yung mga spacing mo dito, no? Ngayon, ano yung reason bakit kailangan mag-pass through yung bato dyan? Para well distributed yung aggregate do sa concrete natin. Kasi pag hindi well distributed yung aggregate natin do sa concrete natin, okay, magiging mahina yung konkreto mo, no? Kasi ang magsasama lang yung semento at buhangin. Pag yan ang nagsama lang, magiging mahina yung konkreto natin. So, hindi yan may consider natin isang solid mass, no? Okay? Isang solid mass kapag walang bato. Okay? So, that's the purpose of this. Now, common 3/4 ang ginagamit na size ng bato. So, 25 millimeters is enough para mag-pass through yung bato, no? Okay, now, that is for flexure member. Kapag naman yung member natin, compression, like column, kapag column yan, kailangan, no, ito yung clear spacing natin. 1.5 diameter of the bar, no? It must be equal or greater than 1.5 inch, whichever is what? Whichever is greater of the two, no? Whichever is greater of the two, yun ang ipa-follow mo. Okay? So yun yung required spacing. Okay, clear spacing, ha? Clear spacing. Okay. So ito, no? Ito yung equivalent metric, no? So 25 millimeter. Okay, so another thing here is concrete cover for cast-in plate. Concrete cover, no? So ito yung distance between so ito yung pinaka distance between yung edge nung section mo, the outside edge, and the reinforcement, no? Yung pinaka reinforcement mo. So kapag yung concrete mo is cast against and permanently in contact with the ground, kailangan ang concrete cover mo ay 75 millimeter. Pag concrete cover ka natin, we are referring to what? Ito yung cover ng reinforcement, no? Para hindi siya directly exposed sa ground. So 75 yan. Kapag exposed to weather or in contact with ground, okay, so kapag yung bakal mo 19 millimeter up to 57 millimeter yan, 50 millimeter yung concrete cover natin. Kapag naman yung bar mo 16 and below, 40 millimeter, no? Now for not exposed to weather or in contact with the ground, kapag ang member mo ay slab, joists or walls, kapag yung reinforcement natin 43, number 43 and up to 57, so these are in millimeter, no? The concrete cover is 40 millimeter. Pag naman number 36 and below or smaller, so 20 millimeter yung concrete cover natin. Now, kapag yung member natin ay beams, columns, pedestal, tension ties, no? The concrete cover is 40. Okay? So, ang reference natin from the stirrup, magbuhat doon sa stirrup hanggang doon sa outer edge ng section mo, 40 millimeter yan. Similarly, ganun din dito sa mga to, no? Okay, yung pinaka-reinforcement mo ang pinaka-basis mo. Okay, to visualize this, ito yon, no? Yung concrete cover natin na yan, beam, columns, no? Yung pinaka-ties, ito yung pinaka-tie mo, ito yung pinaka-stirrup ka natin. So, yung concrete cover mo is measured from the outer edge up to the face of your reinforcement. So, yun yung concrete cover natin. Ngayon yung mga clear spacing ng bawat bar, so minimum of 25. Okay? Now, when we reflect this reinforcement, no, sa beam natin, in the computation, meron tayong tinatawag na effective depth at effective cover. So magkaiba doon sa concrete cover yung effective cover. Ang effective cover, it is what? Measured from the outer edge of your section up to the centroid of your reinforcement. So yung centroid ng reinforcement na binabanggit dito, it referred to the centroid of your group of bar. Okay? So kung isang layer yung bar mo, so yung isang layer, kagaya nito isang layer, no? Ito yung pangalawang layer. So kapag isang layer lang, so yung effective cover mo, it will be measured from the center of the bar up to the outer edge of your section, no? Measured at the bottom, okay? Okay, so yun yung effective cover, okay? Ngayon, kapag dalawang layer yan, so kukunin mo yung centroid ng group of bar. So dun mo i-measure yung effective cover, no? Okay? And the effective depth can be computed by subtracting the effective cover from the total depth of your section. So yun, no? Yun yung ating effective depth. So these things are very important in the analysis and design. So what else? For the working stress design method, so ito yung mga formulas na kailangan natin i-consider. Okay? For the concrete, for normal weight, the computation of the modulus of elasticity of concrete, this is for metric system or SI system. So 4,700 multiplied by the square root of F prime C. Then for the steel, we have 200,000 megapascal. The allowable stresses for our beam in concrete, we have 0.45 F prime C, and our Fs is 0.5 Fy. So ito yung ating mga allowable. Then for the determination of the modulus of rupture for normal weight concrete. So again, this is for SI units, no? SI to. Fr is 0.7 square root of F prime C, no? Then the determination of the modular ratio. The modular ratio designated as N is equal to ES over EC may be taken as the nearest whole number. So, kapag nag-compute ka kung ano yung whole number, yun ang i-consider mo. But, this value must not be less than 6. Okay? So, hindi ka pwedeng bumaba ng 6. Okay, so for the determination of the neutral axis, you can actually make use of this equation, no? That the Q top is equal to Q bottom. So mamaya na makikita natin to kung paano i-apply, no? Yung pagkuha ng neutral axis. Okay, for the transform section, as mentioned a while ago, okay, for uncracked section, okay, wherein MA is less than MCR, our transform section, okay, ito yung ating given beam, ito yung kanyang equivalent transform section. Okay, so yung bakal natin, ita-transform natin siya into its equivalent concrete. So that's basically what this transform section is all about, no? So yung computation ng equivalent concrete area ng ating steel can be computed using this formula. N minus 1 multiplied by AS. AS referring to the area of the steel, the total area of the tensile reinforcement. Yung N dito is the modular ratio. Ito yung ito yon, no? Itong modular ratio, yun yung value ng N dito, no? Okay? So when we compare now the acting moment, the cracking moment, and the allowable moment, okay, ito yung relationship nila, no? So the cracking moment will be greater than the acting moment, whereas the allowable moment of steel will be greater than the cracking moment. So another relationship that we may compare, if your section is a crack, the cracking moment is greater than MA, and MC, which is the allowable moment of concrete, will be greater than MCR. So ito yung about the uncracked section. Now for the cracked section, okay, so the neutral axis, which divide yung ating concrete sa kanyang compression and tension, no? Wherein pag crack na yung section natin below the neutral axis, yung ating konkreto dito crack na, kaya wala na, no? Hindi na natin kino-consider yung below the neutral axis because the concrete here is already cracked. Dito sa uncracked section, bakit natin kinonsider buo yung ating section dito sa transform section natin? Because wala pang crack yung ating konkreto. So dito may crack na, kaya hindi na natin i-consider yung below the neutral axis, no? Okay, and then the equivalent concrete area of our steel can be computed using this formula, N multiplied by AS. So, yun ang pagdating sa crack section. And then, ito yung comparison ngayon. Comparison of our moment, no? Yung moment, yung acting moment natin will be greater than MCR. And MS will be greater than the acting moment. Yung ating acting moment greater than MCR, MC will be greater than MA. So yun yung ating comparison, no? Pagdating sa mga moment and allowable. Okay, so that is about this presentation. So for us to understand the different stages, no, of our beam, no. So we're going to consider here now yung example problem for crack section and for uncrack section. Okay. Nakikita na bang mabuti yung problem? Hello? Andyan ba kayo?
Yes, sir.
Okay. So, nakikitang mabuti yung problem?
Yes, sir.
Okay. Okay, so yung problem number 1 natin is all about uncracked, no? Uncracked reinforced concrete section. So, these are now the given. The length of the beam, 5 meters. The weight, the uniform load is 10 kilonewton per meter. The base, our section is 300 millimeters. Yung depth ng ating section ay 500. Concrete cover, 40 millimeters. The number of bar, 3. The diameter of the bar is 28 millimeters. The diameter of our tie is 10 millimeters. So the strength of the concrete 28. Fy, the strength of our steel is 276. Then the modulus of elasticity of the steel is 200,000 megapascal. We have a given simple beam, no? And the uniform load is acting over the entire length of the beam. So what is required in the problem? Determine the actual moment of the beam. Determine the cracking moment of the beam. Determine if the section is uncracked or cracked. Determine the stresses in the concrete and in the steel due to actual moment. And then you check the adequacy. Okay, so ito yung solution. So for the first requirement, which is the actual moment, it is based from the service load. So tandaan nyo, hindi tayo nagmumultiply ng factor dito, WSD tayo. So the determination of the actual moment, so you basically solve the shear and moment, no? Para makuha mo yan. Okay, so ito ngayon yung ating shear and moment diagram wherein the maximum moment will occur at the midspan of our beam. And when we consider, no, the moment, the maximum moment, it is equal to WL squared over A. So making use of this maximum moment, so this is now our acting moment. Our acting moment is 31.25 kilonewton meter. So ito yung ating acting moment. So ganito tayo kumuha ng actual moment or acting moment. Next, for us to identify, ano ba yung pangalawang requirement? Cracking moment And then after that, we will identify if it is uncracked or cracked. Okay, so for the cracking moment, we will base it from the flexure formula. Ito yung pinaka-flexure formula natin. F is equal to my over I. But since it is a cracking moment, pag cracking moment ka natin, the stress is equal to the modulus of rupture. Ito yung modulus of rupture natin, FR. Then our MCR, then Y, then IG. IG is known as the gross moment of inertia. Then Y is the distance of the tension side, the maximum tension side of your beam up to the neutral axis. No? Yan ang magiging Y natin. Okay, so since we need FR to solve for MCR, so we make use of this formula. No? And FR is 3.7 megapascal. So then after this, we make use of the, we solve for the gross moment of inertia. The determination of the gross moment of inertia, it is based from the section. Yung section natin purely concrete, no? Konkreto lang siya. You neglect the reinforcement. And since it is a rectangle, so we're going to determine the gross moment of inertia with respect to the neutral axis. At merong direct formula for rectangle, and that is pH cubed over 12. No? So ito ngayon yung ating gross moment of inertia. And then for the determination of the location of the neutral axis with respect to the extreme tension fiber, which is your Y. So since you are considering only the concrete part of our section, therefore the neutral axis is located at the mid depth of our section, and that is when we consider the distance Y from the extreme tension fiber up to the neutral axis is equal to H over 2. No? And then isolating MCR and substituting now the known values, our MCR is 46.25 kilonewton meter. Now, making use of the computed MA and this computed MCR, we may able to identify if our section is cracked or uncracked. So since MCR is greater than MA, so therefore our section is uncracked. Okay, so yun yung pangatlong requirement. Then for the fourth requirement, we're going to solve for the stresses. So for the stresses, we're going to consider the transformed section of our beam. So kapag uncracked, ito yung magiging transformed section natin. So the equivalent area, concrete area of our tensile reinforcement can be computed using this formula, N minus 1 AS. Now, we're going to determine the neutral axis of this transformed section. We're going to designate the distance of the neutral axis up to the top as Y top, and from the neutral axis up to the base or up to the bottom of the section as Y bottom. No? Okay, so the determination of the location of the neutral axis, so yan ang una nating gagawin, no? Para makuha natin yung stresses. Okay, so we need to solve the modular ratio, yung N. So it is based from this formula, ES over EC. So we will solve first for EC, okay, using the formula. And this is now the value of our EC. So solving for N, it is equal to 8.042. So we will make use of the whole number, 8. So N now is 8. Then we will solve for the area. the total area of the tensile reinforcement so that makukuha natin yung n minus 1 AS. So this is now the result. And then once we have now this area, we may determine now the location of the neutral axis. So we will refer from the top of the beam, no? So magre-refer tayo dito sa top ng beam natin. So first we need to get the area of the concrete, B multiplied by H, then the location of the centroid of the concrete. So kunin mo lang yung centroid nitong rectangle, which is the mid-height, no? So designated as Y1, and Y1 is equal to H over 2. So that is 250 millimeter. Then for the transformed area of the steel, okay, making use of AS here. So this is the result. And for the location of this, no, yung distance nito, okay, up to the top. So we refer from the centroid of the reinforcement. So i-measure natin yan doon sa centroid ng reinforcement. And this distance, if this line is measured at the bottom, this is called as the effective cover, no? Ang tawag dito ay effective cover, no? Kaya dito makikita natin, we solve for D prime. And D prime is equal to concrete cover plus tie bar plus diameter over 2. So diameter nung reinforcement natin, no? And the result is 64. So Y2 now is equal to H minus D prime. So Y2 is actually known as the effective depth, no? Ito yung pinaka-effective depth natin. Okay, so after knowing Y1, Y2, and the area, okay, so we will consider now yung area total. So to determine now the location of the neutral axis, we make use of the Varignon's theorem. So yung area total, yung moment produced by the total area is equal to the moment produced by the parts, no? So yung part natin, yung A concrete at nung steel. Okay? So ito yung equation natin. And solving for Y top, so it is equal to 264.76 millimeter. So ito yung ating location ng ating neutral axis with respect to the top of the beam, no? Ayan, with respect to the top. Okay? So after knowing the location of the neutral axis, we may now solve the uncracked moment of inertia. So we will refer from the neutral axis. Okay, so since the concrete, which is the rectangle, the centroid of this rectangle do not coincide with the location of the neutral axis. So we're going to use transfer formula in solving for the moment of inertia with respect to the neutral axis, no? Yung ating transformed area for the steel is not also coincide yung kanyang location with the neutral axis, kaya gagamitan din natin siya ng transfer formula. So what we need now here is the distance. Yung distance ng centroid ng concrete with respect to the neutral axis, also the distance of the location of this equivalent or the transformed area of the steel with respect to the neutral axis. So ito yung about this, no? Okay? So yung D representing the distance of the location of the centroid of the concrete up to the neutral axis, and that can be computed using this formula, Y top minus H over 2, no? So i-trace nyo na lang doon sa figure kung ano yung tinatawag natin D1. Area is the area of the section. So, yung concrete is B multiplied by H. Yung IX dito, it represent the moment of inertia of the section with respect to its own to its centroid, no? At ang kanyang formula ay BH cubed over 12. Okay? So ito yung ating formula para sa moment of inertia nung concrete. Ito ay para do sa concrete. Now for the transformed area of the steel, all you need is make use of AD square. AD square lang ang gagamitin mo. So this is the area of the steel, then multiply by the distance D. Okay, so this one can be determined by taking the difference between Y2 and Y top. No? So trace mo lang dito. So that is the distance of this line up to the neutral axis, and that is Y2 minus Y top. Okay? So yun yung ating computation ng moment of inertia, or to be specific, uncracked moment of inertia. So substitute, then the result. So you have your uncracked moment of inertia. Then after this, you may solve now the stresses because you already have now the uncracked moment of inertia and also your distance, no? So ito yon, no? To determine FC, okay, using Flexural formula, so our stresses is based from the acting moment, no? Kaya ang ilalagay mo dito ay MA. So yung distance ng FC, ayan, up to the neutral axis is Y top. Kaya Y top tayo doon. And this is now the resulting stress, no, for concrete. So this is the maximum stress in our concrete. Then for the tension in the concrete, FT, ang distance niya from the neutral axis is Y bottom. Okay? So actually ayan yung Y bottom. And Y bottom can be computed by taking the difference between H and Y top. Ayan. So substituting the known values, your F sub T, which is the tension, the tensile stress in the concrete, no? Dahil uncracked pa to, so we still have no values for this. So 2.08 megapascal. Now, as I have mentioned do sa discussion natin do sa Flexural, kapag uncracked yung section natin, meron pa tayong isang criteria na pwede nating maging basis, no? Ito yon. When the tensile stress in the concrete is less than the modulus of rupture, you have an uncracked section. So itong criteria to, ang problema nga lang niya, kailangan na-compute mo na, no, yung mga stresses. Unlike when you compare MA and MCR, kaagad, no, ma-identify mo na uncracked yan, no? Okay, how about the stresses in the steel? Ayan. The stresses in the steel, since the moment of inertia is based from the transformed section, so our stress in the steel will be divided by N, no? So it will be divided by N. And the distance of our Fs over N is Y2 minus Y top, no? So it is Y2 minus Y top. So yan, no? Pasok mo siya doon. And the result is 12.1 megapascal. So ganun yung ating stresses, no? Okay? So that is for the stresses in the concrete and in the steel. Now, for the adequacy, no? Yung para sa adequacy naman, okay, we're going to compare the actual stresses and the allowable. So our actual stress in the concrete is 2.34. So dito galing yan. Ayan, no, yung na-compute. So you compare it to the allowable stress in concrete, which is 0.45 F prime C. So 12.6 yun, 2.3 it is less than. So ibig sabihin hindi tayo lumagpas do sa allowable. So therefore okay yung ating beam, no? Then for the steel, our Fs is 12.1, ayun. Compare natin dun sa allowable, 0.5 Fy, it is equal to 138. So therefore, hindi rin tayo lumagpas sa allowable. So okay din yung computation natin. So therefore, we can say na safe yung ating section. So that's how we compute, no? The requirement, no, if our section is uncracked, no? So ito yung isang example natin. Okay, next, no? So tandaan natin, kailangan na marunong kayong kumuha ng moment, which is the maximum moment, no? Okay? Then also, you should know how to determine gross moment of inertia, no? Pure concrete. Huwag mo munang include yung steel, no? So kailangan kunin mo yan dun sa centroid nung section, no? Pagkatapos nun, no, kukunin mo yung location, no, yung distance ng extreme tension fiber with respect to the neutral axis of this section. Okay, walang reinforcement, ha? Pagkatapos niyan, you should know how to obtain the transform section for our given beam if it is uncracked, no? So all you need is solve the area, and then also, no, you need to solve for the location of the neutral axis, and eventually masosolve mo yung moment of inertia. Okay, so I think by following the procedure given here, this one may serve you as a guide, no, in computing for the following requirement for uncracked section. Okay, so let's proceed, no, to the next problem. Yung next problem natin is a crack section. Okay, crack section naman tayo, no? Okay, so ano yung bago dito, no? Ano yung pinalitan? So same beam, no? Same beam, same section, only differ in the load. Ang load ngayon dito ay concentrated load 60 kN. Ito ngayon yung ating beam. So same beam, same section, so same lahat, no? Pera lang yung load. So ang gagawin natin ngayon, same requirement. Pareho yung requirement natin, no? Okay. So for the determination of the actual moment or acting moment, so you may draw the shear and moment diagram and then determine the maximum moment. The maximum moment is PL over 4. So PL over 4, so 75 kilonewton meter. Okay? So yun yung ating acting moment. And then for the cracking moment, kamukha lang nung ginawa natin kanina, no? Kung paano natin kinumpute kanina dahil the same section tayo. Ayan, ang cracking moment natin ay 46.25. Ang ating acting moment ay 75. So this time, the acting moment is greater than MCR. So therefore, our section is cracked. So crack na ngayon, no? So kapag crack yan, Ito ngayon yung transform section ng beam, no? So wala na yung ibaba, no? So this is now the equivalent transform section. Now, for the location of the neutral axis, I designate here KD. KD yung designation natin, no? Okay? So ngayon, para makuha natin yung location ng neutral axis, kagaya nung dati, no? Isosolve natin yung modulus of elasticity ng concrete, modular ratio, area of the steel, no? This time, it's no longer n minus 1, but rather NAS. Okay, kaya naka-multiply na lang siya ng 8, no? So, NAS. Sorry for that, no? Ano pala to? Area pala to, sorry. Area of the steel. So, mamaya pa lang yung NAS, no? Sorry, ito. NAS. Okay, so this for the total area of the steel reinforcement, no? Okay, so for the location of the neutral axis, again, we will refer from the top. So, isosolve natin yung KD, no? Yung KD. So, this for the area of the concrete, and since ito na lang yung concrete na i-consider natin, so yung centroid nito will be 1/2 of KD. Yun yung magiging Y1 natin. Ayan. KD over 2, no? Then for the steel, NAS na lang, hindi na N minus 1, no? Tapos for the location of our transform area for the steel, so magbuhat dito hanggang doon. So since same beam tayo, so pareho lang yung computation do sa unang problem, no? Okay, so ito yan, no? D is equal to H minus concrete cover. Ito yung D prime. No, ito yung D prime, no? So hindi ko na ni-reflect dito yung D prime. So diniretso ko na, no? Sinubtract ko na yung equivalent ng D prime. So ito na ngayon, no? So this now our D. Our D is actually Y2. Ito rin yung Y2 dito do sa problem number 1, no? Do sa problem number 1 nilagay natin Y2. Dito ginawa ko na siya ng D, which is the effective depth, no? Ayan mismo. Okay. We solve now for the total area, and then after that we use Varignon's theorem for the determination of KD. So this time, no, yung equation mo na mapoproduce ay quadratic equation. So you're going to simplify your equation. So you're going to do this in your work, sa mga exams, sa mga laboratory work. Walang shortcut, ha? Okay, walang shortcut. Kailangan ipakita nyo kung paano nyo kinuha yung KD, paano nyo sinimplify, and also you reflect yung paggamit ng quadratic formula. So, kailangan naka-reflect to. Kapag hindi ito naka-reflect sa mga computation nyo, I will not consider anymore yung mga susunod na result dito pag ginamit mo yung KD. No? So, kailangan ipakita nyo mabuti sa akin kung paano nyo nakuha yung KD. No? Okay? So, kailangan i-reflect yan. So, this is now the resulting value of KD. So, since crack yung section natin, ang kukunin nating moment of inertia ay crack moment of inertia. So, again, you go back to your transform section and then solve for the moment of inertia, no? Itong mga naka-shade na part, ito ang kukuhanan mo ng moment of inertia with respect to the neutral axis. And look at this. Yung rectangle natin, yung kanyang base is exactly located kung saan yung neutral axis. So, meron tayong formula, no? Kung paano directly kunin yung rectangle kung ang moment na kinukuha natin is exactly located dun sa kanyang base, yung pinaka-bottom ng rectangle. At ano yung formulang yon? At ang formulang yon ay ito, no? Okay, we have BKD cube over 3. Actually, no, itong naka-reflect kong formula dito, it's not what appropriate. It should be like this, no? So ito dapat diretso, no? Ito mismo, no? Ito mismo yung magiging formula mo, no? BKD cube over 3. So sa mga libro, we have yung BH cube over 3. Okay? So ito yung magiging moment of inertia ng concrete. For the steel, we have NAS multiplied by D minus KD square. So yung D minus KD square, ito yung distance nitong centroid nito up to the neutral axis, and that is D minus KD. Ito yung distance na yun, no? Okay? So yun yung about this moment of inertia, no? So this is now area multiplied by D square, no? Ito yung pinaka-D natin, D square. So substituting the known values, okay, the result is this one, no? So ICR. Okay, next, after knowing ICR and after knowing the location of the neutral axis, we may now solve the stresses, no? Okay, for crack section, wala na yung F sub T. So it will be F sub C and F sub S na lang, no? So for the concrete, the distance of FC with respect to the neutral axis is KD. Kaya KD yung ilalagay mo doon. Okay, and our FC is 8 megapascal. Now for the steel, ang distance ng steel up to the neutral axis is D minus KD. Kaya yun, no? Ito ngayon yung result. 106.45 megapascal. So that's how we solve the stresses in our concrete and in our steel, no? Making use of the stress diagram. And then for the allowable moment, no? So for the allowable moment, okay, so ito yung pinaka-solution natin, no? This is one of the method na pwede mong gamitin. Now, if you want to solve for the allowable moment for concrete, so we make use of the flexure formula. But our flexure stress should be equated to the FC allowable. Our FC allowable is 0.45 F prime C. Okay? So then you may solve for MC. Okay, now another solution for us to solve MC, ang gagawin mo, magmo-moment ka, no? Itong C natin, imo-moment natin with respect to T. So ito, no? C, imo-moment natin with respect to T. Ang moment arm niya ay D minus KD over 3. And C is computed, no? Ito, no? Ito yung ating formula, no? Okay, yung natin, ito yung effective depth, no? Effective depth. Ito rin yung na-compute natin kanina dito. Ayan, no? Ito rin yung na-compute natin dito. Okay? So, effective depth. But I already put the detailed computation of T here. Then your C can be computed using 1/2 0.45 F prime C multiplied by B multiplied by KD. So yung 0.45 F prime C is actually your allowable, no? Yung allowable mo, yun. Okay, pasok mo lang dyan. Then, okay, yung pinaka moment produced by C. Ito yung moment produced by C, no? So yun ang moment C natin, no? Moment C natin. Okay, so substitute mo value ng C, yung value ng D minus KD over 3, and the result is 118.05. So almost the same, no? Yung ating MC. Okay? So that is our allowable moment. Now for the allowable moment in steel, okay, yung isang method o isang solution, we make use of the Flexural formula. But this time, yung ating stress sa steel, we will make use of Fs allowable over M. And Fs allowable is 0.5 Fy. So substitute natin dito and then isolate Ms. Your result is 97.23 kilonewton meter. Now, the alternative solution, if we go back here, ito, no? I-moment mo yung T with respect to C. Ang moment arm D minus KD over 3, no? Okay, by the way, bakit KD over 3? So, the stress diagram of our concrete is triangular. So, when you put a compressive force here, its location is 1/3. Dahil yun ang centroid ng triangle, no? So, 1/3 at the top. Kaya meron tayong KD over 3 doon. Okay. For the steel, the alternative solution, ito yun, no? Okay. Our T can be computed using AS multiplied by 0.5 Fy. Then, ito yung pinaka-moment produced by our tension force, no? So, substituting the known values, it will give you the same result. Okay, so it's up to you kung ano yung gusto nyong gamitin in solving for the allowable moment in concrete and in the steel, no? So, kahit sino sa dalawa, pwede yan, no? So, now, since we are computing for the allowable moment, no? That is basically the safe allowable moment, no? So we're going to compare MC and MS. Iko-compare mo yung dalawa, no? And then you select the allowable moment. Ano yung allowable moment natin ngayon? Yung mas maliit ang value. So the allowable moment, you select the smaller value between MC and MS. And the allowable moment for our section is 97.23 kilonewton meter. So meron itong kilonewton meter, no? So, nakalimutan natin. Kilonewton meter. Okay? So this is in kilonewton meter. Okay, so after knowing the allowable moment, so let us check now the adequacy. Okay, so all you need is compare, no? Yung actual stress at saka allowable, kailangan less than. Fs is less than the allowable, so okay, no? So from stresses, we can say that the beam is safe. Now for the moment, no? Yung acting moment at allowable moment, i-compare natin. Kailangan yung allowable moment mo is greater than the acting moment. for you to say na safe yung beam mo. So it shows here that the allowable moment is greater than the acting moment. So ibig sabihin ngayon, nung allowable moment, ito yung capacity. Ito yung capacity nung beam natin, yung section ng beam natin. No? Ang kaya niyang moment ay hanggang 97.23 megapascal. Yung naka-apply na load sa kanya, ang moment na na-produce lang ng load is only 75. So ibig sabihin, kakayanin niyang i-carry yung load because its capacity is up to 97.3 megapascal. Sorry, it's not megapascal. So sorry to, no? So this is not megapascal, but rather Newton meter. About that, nag-close yung program, naka-encounter ng error. So I'm going to open again, no? So ito, no? Okay, nakikita nyo ba uli yung ating nakikita na ba?
Yes.
Okay,
Yes,
so ito,
sir.
no? So the capacity is more than the applied, no? So that is why the beam can carry the load, the given load. So that is why our beam is safe. Okay? So yun yung about the problem number 2, no? Okay, so which is all about crack section. Okay, so both problem 1 and 2 are rectangular section. Okay, so both are rectangular now. Yung next problem na ipipresent ko, I'm going to present a T section, no? T section. Okay. So ito yung next problem natin. Nakikita na ba yung problem number 3? Okay, so yung problem number 3 natin, our section is a T section. Okay, T beams ka natin, no? Ang requirement natin, location of the neutral axis in terms of AD, then determine the crack moment of inertia, determine the stresses in the concrete and the steel, determine the allowable moment, and check the adequacy. Now, if we're going to consider this problem, ang pinagkaiba lang niya yung section. Yung section lang, no? Okay? Compare it to problem number 2, no? So if this is a crack section, no? Okay, if this is a crack section, okay, assumption is that this is a crack section, no? So walang nakalagay sa problem, but anyway, we will consider it as a crack section, no? Okay, so ito yung mga bakal niya, anim na number 36 in two layer, no? In two layer yan, ha? Okay, then these are the designation. BW referring to the width of the web, which is equal to 350. Yung total depth natin ay 560. Yung BF natin referring to the width of the flange, 800. And then TF is the thickness of the flange. Okay? So yun yung ating, then yung acting moment is already given, 250. So dito natin malalaman kung crack, no? But anyway, I already told you that this problem is a crack section, no? So given yung MA natin, hindi na yan i-compute but rather given. So ngayon para ma-prove natin, no, kung talagang crack ito, we're going to solve for the cracking moment, okay? Hindi na pinakita dito sa problem, no? So anyway, yung yung ano natin, no? Yung ating cracking moment, no? So since hindi na yan pinakita, ang assumption kasi dito, it's already a crack section, no? So anyway, mukhang hindi na pinakita, no? The assumption here is that the beam is a crack section kasi napakalaki ng moment, no? Yung moment actual natin or acting moment natin napakalaki. So it will be more than the cracking moment. Kaya crack section tayo automatic. Okay, so let us solve now the neutral axis, no? So ito lang yung magiging pagbabago, no? Kapag crack yan, so yung tension part ng ating concrete will be neglected, only the compressive, no? So kung ano lang yung under compression, yun lang yung consider natin. Now, ang assumption dito, yung neutral axis natin is on the web. Nasa web. Wala siya sa flange, no? So nasa web. Yan ang assumption natin. And we will check that kung tama yung assumption natin, ha? Okay, so the assumption is that the location of the neutral axis is on the web, ha? Okay, so ito ngayon, no? Look at here now. Look at our transform area for our steel. Ang ginawa dito, nilocate nila yung centroid ng group of bar. At doon nilagay ngayon yung equivalent area ng ating steel. And the computation is NAS. Kaya lang, AS1, AS2 tayo dahil it referred to the first layer and to the second layer. So ganon. Tapos yung pagkuha natin ng KD, we need to consider the centroid. Yung centroid ng mga divided rectangle dito sa ating transform section, no? So we divide it into two, no? We have this one at saka yung dalawa dito. So since similar itong dalawa, so we will just multiply them by 2, no? So the centroid of this flange, ang kanyang distance from the top ay y1, while itong rectangle na to, which is the web, ang centroid niya from the top ay y2. And then ito namang steel natin, ang distance niya from the top is d, which is the effective depth, no? Effective depth. So y3 here is actually your effective cover. Effective cover ito, no? Itong ating y3. Okay, so for the computation, again, no, you need to solve this following modular ratio, modulus of elasticity of concrete, the area of the steel. Then we're going to consider yung dalawang divided parts ng ating concrete. We call it A concrete 1 and A concrete 2. No? So ito sila. And then yung computation ng Y1 and Y2. So we have here. And the transformed area of the steel. So this is now the equivalent. Okay. So now, for us to determine the location or the distance of the transformed area of the steel or the equivalent area of the steel, so we need to solve for Y3. Y3 representing the location of the centroid of the group of bars, no? So ito yung ating computation. So yung ating unang layer, ang distance niya from the bottom is 80, while itong second layer, ang distance niya from the bottom ay 180. So ang gagawin natin, i-moment natin, no? So we make use of Varignon's theorem. Minoment natin itong dalawang layer ng bar with respect to the bottom. So ang result ay 130. So therefore, the distance of the group of steel, no, with respect to the top is what? D equal to H minus Y3. So D now is 430. So the total area, and solving now for the location of the neutral axis, we make use of the Varignon's theorem. Okay, so substitute mo yung mga known values, you simplify, and then use quadratic formula. Dahil lang mapoproduce mo ay quadratic equation. No? Okay, another solution. Ito yung kanina, yung sinasabi ko sa inyo. Q top equal to Q bottom. So paano yan? Itong nasa taas na to, i-moment mo with respect to the neutral axis. Ito nga yung equivalent steel natin, i-moment mo with respect to the neutral axis. Kaya ang tawag natin dito ay Q top, ito naman yung Q bottom natin. No? So yun yung about this. No? So para at least makita nyo ano yung Q top equal to Q bottom. Ayan, no? So ito yung concrete natin. Yung KD minus 40 is actually the distance nung centroid up to the neutral axis. Ito naman, KD over 2, ito yung distance niya from the centroid up to the neutral axis. No? And then ito naman yung ating steel. Yung area ng steel natin, ito naman yung distance niya from the neutral axis. No? So D minus KD. Again, when you substitute the known values here and you simplify, pareho lang yung lalabas na equation. No? Kapareho dito at saka doon. No? Pareho yan. So the same result ang makukuha mo. No? Kaya it's up to you if you want to use Varignon's theorem or yung Q top equal to Q bottom. Ha? So nasa inyo yan. Okay, so after knowing your the location of the neutral axis, we may solve now the moment of inertia. No? Yung ating flange, itong flange natin dito, hindi nag-coincide yung kanyang centroid. Hindi nag-coincide yung kanyang centroid with respect to the neutral axis. So therefore, we're going to use transfer formula, no? Transfer formula ang gagamitin natin. Ito. So ito 'yon, no? So BF minus BW okay, BF minus BW is the base, no? Base nun. Yung kanyang altitude ay TF. Kaya ito yung BH cube over 12. Ha? So then plus the area, yung area nung ating yung area nung ating flange, no? So makikita nyo dito BF minus BW. So ibig sabihin pinagsama na. Pinagsama na itong dalawang to, no? BF minus BW. So ginawang isang rectangle na lang to. Itong dalawa dito, no? Yung flange, no? Tapos ito ngayon, isang rectangle uli. Again, no, itong rectangle na to, ang kanyang moment, no, with respect to the neutral axis, eksakto yung kanyang base. Eksakto yung kanyang base, no? Kaya kapag kinuha natin yan, ang formula natin ay, ayan, BH cube over 3. Ito yung kanyang altitude, ito yung kanyang base, then divide 3, no? Yung flange kanina, ito yung kanyang area, yung kanyang width, ito yung kanyang altitude, at ito yung kanyang d square. No? Ito yung kanyang d square, no? So this is the d square. So it is kd minus tf over 2 square, no? Tapos ito yung rectangle na merong bw. Ito yung kanyang moment of inertia with respect to the neutral axis. And then, yung ating still, no? Ang kanyang distance from the neutral axis ay d minus kd. So we simply make use of kd square. Ito yung area, ito yung d. So naka-square siya, no? So ito yung kanyang crack moment of inertia nung ating transform section para sa ating T-beam, no? So substitute mo yung mga known values, your ICR is equal to ito ngayon, no? And then after this, you may solve, no, the stresses. So ito, no? I think you can easily follow now this, no? Even though wala na akong diagram dito. So I already presented it, no, do sa problem 1 and 2, no? Kung paano kinukuha. And then for the allowable moment, so again, I make use of the Flexural formula. No? Similarly, ganun din do sa steel. And then we select whichever is the smaller of the two, no? So ang allowable moment natin ay 294.59. And then to check the adequacy, okay, the allowable, no, in our FC1 and FS2. Yung FS1 natin, ito yung first layer, no? Yung FS2, ito yung pangalawang layer, no? Okay. So, eto, no? Ito yung unang layer, ito yung pangalawang layer, ha? So, yun yung pagkakakuha natin, no? And then, for the moment, so lumilitaw lahat ng mga stresses natin less than the allowable. So, okay, safe yung beam natin in terms of the stresses. Now, in terms of the moment, the acting moment must be less than the allowable. It shows here that the allowable is greater than the acting, no? So therefore, we may conclude now that our beam is safe. Okay, so that will be the solution, no? So I think your biggest problem now here is yung pagkuha ng neutral axis, no? Also, no, yung paglocate ng neutral axis. So you will have to read, no, kung paano kumuha ng centroid, no? Kaya napaka-importante na itinuro yung pagkuha ng centroid sa statics, no? Okay, I think ito naituro ko na to so sa mga estudyante ko sa ano no sa mechanics of deformable bodies. Problem is, okay, ngayon pagdating dun sa moment of inertia. Okay? So yan dapat tinuro din yan sa statics, no? Yung ating tinatawag na moment of inertia, no? So, yung paggamit ng transfer formula. Okay, so probably yun ang mga bagay na may experience nyo na difficulty in case of you are not familiar, no? Yung pagkuha ng cracking moment, yung pagkuha ng uncrack moment of inertia, no? Yung crack moment of inertia or uncrack moment of inertia, then the location of the neutral axis. Yung part na medyo mabigat-bigat, no? But the rest, you may simply follow yung formula, no? And once you have the location of your neutral axis, once na meron ka na nun, so you may able to determine easily, no? Yung mga stresses, no? Okay? And even the allowable moment. Okay? So yun yung so far, no, na nakikita ko na medyo makaka-experience kayo ng difficulty, no? Now, I'm done with the problem number 3 question. Before I proceed to problem number 4. Any question? Question? We still have 45 minutes, no? In our lecture. Dahil hanggang 3 o'clock tayo. Any question? Okay, so walang nagre-react. Kasi mamaya, after my lecture, I'm going to give you your laboratory exercise number 1, no? Yung laboratory exercise number 1 nyo, it will be given mamayang 3:30, no? Pagkatapos isasubmit yan tomorrow. So you are given 2 days or 2 meetings for you to finish the laboratory work. Now, since matatapos ko yung lecture today, no? Matatapos ko yung lecture today. So therefore, no, tomorrow it will be your quiz number 1. So meron kayong quiz number 1 tomorrow, and the coverage is all about what? From the beginning up to kung ano yung matapos ko ngayon, no? So that will be the coverage of your quiz 1. Okay? So that will be tomorrow, no? The quiz will start at 12:30, no? Okay, so I will give time, no, sa mga item na ibibigay ko, and then no, after that, after the quiz, you finish your laboratory, and then isasubmit nyo yan tomorrow lahat, no? Okay, so since walang question, I will move on to the next problem. Yung problem natin, problem number 4. Okay, problem number 4 is actually a double reinforced beam. Okay? Yung mga kinonsider natin na beam from problem number 1, 2, and 3, those are considered as singly reinforced beam. No, mga singly reinforced yun. Ibig sabihin, ang reinforcement nila nasa tension lang. Nasa tension lang, no? Ngayon, merong beam na tinatawag na doubly reinforced. Meron siyang reinforcement sa tension, meron siyang reinforcement sa compression. So kailan ginagamit ito? Ginagamit ito kapag limited yung depth. Limited yung depth ng section mo at malaki yung moment mo. Okay? So malaki yung moment mo, tapos limited yung depth, no? Yung architect mo ayaw niya ng malaking beam. So ngayon para malimit yung beam mo at magamit mo yon, so gagamit ka ngayon doubly reinforced, no? So that's the use of the doubly reinforced. Okay? So ngayon ito yung given problem. So doubly reinforced. Okay? So the given acting moment is 150. Okay? The tension reinforcement is given in two layer, no? There's a 3 number 28 in the first layer, then 2 number 28 in the second layer. Now for the compression reinforcement, we have 2 number 28, no? 2 number 28 at the compression reinforcement. So this is the dimension of our beam, no? Then given already here yung ating modular ratio, no? Given na kaagad, no? Number 8, ha? Okay, so let us compute. Okay, so the equivalent or the transformed area of our section, if this is a crack section, no, kapag crack, no, ito yung kanyang equivalent, no? So mapapansin natin, ito yung sa concrete, tapos ito naman yung para sa steel, no? Para sa compression steel. The area of the compression steel can be computed using n-1 AS. So katulad din ito nung kanina, no? Ito sa uncrack, no? n-1. So dahil nasa compression siya, okay? Dahil uncrack, no? Sorry. Dahil uncrack ito, so it is equal to n-1 AS, no? Now for the tension reinforcement, so we make use of the n multiplied by AS1 plus AS2, and the location of this is based from the centroid of this group of bar, no? So kagaya ng ginawa din natin kanina sa problem number 3, sinolve natin yung location nito. So this time ang kanyang location D prime. Ito na, no? Ito yung D prime. Ito yung tinatawag nating effective cover, no? Effective cover. So this is how we determine the effective cover kapag two-layer tayo, no? So kagaya ng problem number 3, no? Ganun na ganun natin siyang isosolve. Okay? So ito ngayon yung computation natin, no? I will not elaborate anymore dahil halos yung ating procedure, straightforward yung procedure natin, no? Nagbabari lang pagdating dun sa computation ng neutral axis, dun sa cracking moment of inertia. So dun lang nagbabago, no? And the rest the same, no? Okay, so eto ngayon, area ng steel, area of the concrete, then the location of the centroid of the concrete with respect to the top, no? So KD over 2. Now for the tension bar, ito yung area natin sa tension bar. Do sa compression bar, ito naman yung area natin. Now solving for the location ng ating tension bar, no? Yun yung tinatawag nating D prime, no? So how do we solve for okay, so how do we determine yung location o yung D prime, yung effective cover natin, no? For the tension reinforcement, ito yung computation natin, no? Area total multiply by the D prime, then AS1 multiply by 75 plus AS2 multiply by 150. Saan yun? Ito, no? Kapag kinonsider natin ito, okay, yung D prime ito, yung distance nitong tatlong bar na to, 75, yung distance nitong dalawa is 150. Okay? So, kinukuha natin yung centroid ng group of bar, which is known as your D prime. So, D prime yan, no? So, ang tawag dyan ay D prime. So, using Varignon's theorem, okay, and solving for D prime now, the result is 105 millimeter, no? So, it is equal to 105 millimeter. Now, for your compression reinforcement, ano naman yung distance niya from the top? Ayan, given na, no? 75 millimeter. Okay? So, given na siya. Kaya yun siya, no? D double prime, 75. So, we designate the distance of the compression bar up to the top as D double prime. So, ang tawag din dito, effective cover sa compression. Itong D prime naman, effective cover para sa tension reinforcement. Ha? Okay? So, determination now of the effective depth. Ang effective depth, kukunin mo yan with respect to the effective cover dun sa tension. Ayan, D prime. Dun sa tension yan, hindi dun sa compression. Ha? Dun sa tension. So, ito yung ating D. And then solving for the total area of our transform section, ito yung ating total area, unknown to KD. No? So, using now Varignon's theorem, again, no? You substitute the known values, then you simplify. Then use quadratic formula. So, ito ngayon yung resulting KD natin. No? And then, after that, you solve now the moment of the crack moment of inertia. No? Ito yon, the crack moment of inertia. Again, if we're going to look at the our transform section, yung ating itong ating concrete, exactly yung base niya located with respect to the neutral axis, kaya ang gagamitin natin dito ay BH cube over 3, no? Pero itong ating compression reinforcement, yung kanyang centroid hindi coincide with the neutral axis. So, meron tayong D. Gagamit tayo ngayon ng transfer formula. Similarly, ganun din dito sa tension reinforcement natin. Hindi coincide yung centroid nito with respect to the neutral axis. So, meron siyang corresponding D distance. So, gagamit tayo ng transfer formula para dito. Kaya yung ating equation for the crack moment of inertia, ito yung sa concrete rectangle, BH cube over 3, and then dun sa ating compression reinforcement, ito yung kanyang D distance, KD minus D double prime, no? Tapos yung sa tension reinforcement, ito yung area nung equivalent area ng ating tension reinforcement. Ito naman yung kanyang D distance, D minus KD. So substitute the known values. This will be now your crack moment of inertia. And then we have now stresses. Now once you have your ICR, your location for your moment of location for your neutral axis, you may solve now for FC. So ito ngayon yung result. For the compression reinforcement, the stress is equal to 49.42. And then for the first layer of tension reinforcement, and then for the second layer, we have this. Okay, so I think yun yung requirement, no? Do sa ating problem. Okay, so which is up to the stresses, because what is required here is only the flexural stresses, no? So hindi ni-require yung allowable moment, hindi pina-check yung adequacy. It's only the stresses. So this is the solution of problem number 4. Okay, so this problem number 4. Nawala yung number 4 dito. Okay, so I'm done with my lecture for WSD. So ito yung lecture natin sa WSD, no? We will not design beams using working stress method. We only analyze, no? Mag-analyze lang tayo kasi it is not it's no longer allowed by the code na magdi-design tayo ng building using the WSD method. We will only use the concept, the principle of WSD when we check for what? Serviceability requirement. So doon lang natin gagamitin yon, no? Pero pag design, the code require us to use strength design method. Kaya yung susunod na lesson natin yan will be all about strength design method, no? So doon natin ngayon makikita yung design part, no? Yung analysis and design, no? But for WSD, we will simply analyze. Now, why is it we need to include this? As I have mentioned, in the design of beams, we usually check yung tinatawag nating deflection, no? And cracks, no? Wherein pagdating sa deflection, we need moment of inertia. At ang pagkuha ng deflection is based from serviceability requirement, no? And that is based from the WSD method. So ibig sabihin, yung pagkuha natin dito ng centroid, yung paggawa natin ng transform section, yung pagkuha natin ng moment of inertia, gagamitin uli natin ito pagdating natin sa serviceability requirement, no? Sa design ng beam. Kaya obligado kayong pag-aralan nito, no? So you are required to study this, no? Actually yung pagkuha ng centroid at pagkuha ng moment of inertia, dapat yan matagal nyo nang napag-aralan yan, no? Dapat yan tinuro na yan, no? sa statics, no? Dahil pagdating mo ng mechanics of deformable bodies, ginagamit mo rin uli, no? Di ba? I think na-experience nyo yan, no? Ginamit din yan uli, no? Kaya dapat statics pa lang tinuro na yan. Okay? Kaya wag nating sabihin na bago. Bago yung topic na yan, no? Kundi dapat matagal nang tinuro at matagal nyo nang alam. Umabot kayo ng RC, ibig sabihin na-encounter nyo to sa mechanics of deformable bodies, no? Okay? So I'm done with my lesson with WSD. So our next lecture will be all about analysis of beams using strength design method, no? So pupunta na tayo sa strength design method. Then pagkatapos ng analysis, we're going to design, no? So magdi-design naman tayo. So bali dalawa 'yon, no? Okay. So I'm going to check now the attendance. Kung meron kayong tanong